In the name of God, the compassionate, the merciful. Engineering Plasticity, Chapter 2, Stress Analysis, Part 7. So far, we have found that what is the three-dimensional state of stress on an arbitrary plane for an arbitrary stress vector. Also, we found out how to determine the principal stresses, their directions, and how many principal stresses are there. And we found out that there are three principal stresses, and we have three planes and three principal stresses. Now, this was the equation that we obtained. This equation, as you can see, is a third degree equation. So it has three roots, which are sigma 1, sigma 2, and sigma 3, the principal stresses. What we want to talk about now is the stress invariance. Stress invariance. Invariance means the things that are not varying. They are constant, okay? So if you look at this equation, we have some coefficient here, this parenthesis. As you can see here, we have substituted for the parenthesis like that as I1, I2, and I3, okay? These three parentheses. Now, we are saying that I1, I2, I3 are invariants. They are not varying. They are not varying with what? With the change of axis. We are going to show that I1, I2, I3 are constants as regards the change of axis. Okay. We want to show I1, I2, I3 are invariants, meaning that they are independent of the coordinate axis. This is the case if. So that's what we want to prove. We want to prove that these coefficients, these parentheses, I1, I2, I3, are not varying with the coordinate axis. What does it mean? It means that on different coordinate axes, their value remains the same. Okay? So like that. So if we use the Cartesian axis, I1 is sigma x6, sigma y, sigma z. Therefore, if we use another axis like that, okay, or the principal axes are 1, 2, and 3. Any kind of axis, if we use for sigma I is the same. Sigma x6, y, z is sigma I. Because x, y, z, I changes from x to z, so I means x, y, z. And therefore, if we could prove this, if we could prove that the value of sigma on different axes is the same, I mean the sum of these values are the same, then it is proven that I1 is an invariant, independent of the coordinate axis. How could we do that? We are going to use this equation which we obtained in slide 41. If you remember, when I obtained this, I said that we use this for transformation, coordinate transformation, and I said that we are going to use it. It's very important equation. Now I explain it in a moment. Therefore, what we want to do here, you see Sn is the normal stress to the plane, and sigma x6, y, z, xy, yz, and x and zx are the components of the general state of stress. Now in here we have x, y, z. So this is the x, y, z coordinates as written here. But here we have different kinds of coordinates. Okay, so this is xi, eta, and zeta, and this is 1, 2, and 3. So any axis of coordinates. So how do we use this equation to prove this? How do we do that? Now, in order to show that, I have to explain a bit about this equation. This equation, if you remember, we had this stress, general state of stress, on an arbitrary plane, and this was Sn was the normal component of the stress. But if you look at Sn, the direction of Sn is On, okay? It's perpendicular to this plane, and it makes an angle to z-axis, okay? Also to x-axis and y-axis. Now, if we have another plane in another direction, so that this n could be in another direction like that, also in two other directions perpendicular to On, okay, then we will have three set of axes that are perpendicular to each other and make an arbitrary angle to xyz, to the Cartesian coordinates. So for this one, I have the transformation here. Sn is equal to that. It means that if I have the components on x, y, z, I can get the stress on one vector or one direction On using this equation. Then if this On is one of the axes, then the other two axes will be similar to On, and I can get the SS value on those vectors as well, and then add them together and see if they are equal. Okay, so let's do that. Now here I have shown another set of axes. You see, we have this axis x, y, and z. This is the Cartesian coordinates. Now we have another set of axes, xi, eta, and zeta axes, and they make angles with different axes. For instance, with the x-axis, they make these angles L xi. It means the axis xi makes an angle arc cos Lxi with x, and eta makes arc cos L eta with x, and zeta makes arc cos L zeta with x. Similarly, they can make m xi, m eta, and m zeta with y-axis, and n also with the z-axis. Okay, so these are the angles that these axes make with each other. Now we have Sn for the Cartesian axis, but we can have we could change this n, supposing n is this one, because I get back to this, because n is On, okay, On. So Sn could be any vector, stress vector, and On could be any direction, because we took this as a general plane and we took S as a general stress state. So On is a generalized vector line making an angle with these xyz axis, and so this is a general equation. Therefore, if this is so, we can use this n S xi is equal to sigma xx L xi, and so on. See, we are obtaining this S xi in terms of these components, okay, because this Sn was a generalized line, so is S xi xi, and this L was the direction cosine of ON, so this is direction cosine of xi, right? So that's how we can make the transformation between one axis and these all the components of stress in the general state of stress. And also we could use similar equations for zeta and eta. Okay, similar equation for zeta and eta, and for all of these, the direction cosines, of course, we have these relationships. The square roots of these direction cosines of 1, and if we take the product of the direction cosines, they must be 0. So using these equations, then we can show that I11 is equal to that. If you how could we do that? If you put instead of S this expression, put it there, okay, for xi xi, and then for zeta zeta, put it there. Also for eta eta, put it there. We will get a very long expression in terms of sigma x6, sigma yy, sigma zz, and then as you can see here, we have sigma xx, and also here we have sigma x6, so that if we add up this sigma xi, eta and zeta together, L zeta xi squared, L eta squared, and L zeta squared. And similarly for sigma yy we get this one, and for sigma z we get that one. And using these two equations, you can see that these are all equal to 1, and so we get sigma xi xi, sigma eta eta, sigma zeta zeta equal to sigma x6 y z because these parentheses are equal to 1, and so we get that. Similarly for 1, 2 and 3, supposing 1, 2 and 3 are axes like that, similarly for that we get we could use the same transformation and we get the same result. So this is how to prove the invariance. We have proved that I1, the first invariant, is invariant. We have shown here that it's independent of the coordinate axis. It means that any coordinate axis that you use, it doesn't matter. You get the same results. I1 is the same. Okay? Right then. Let's see similar expressions for I2 and I3 we can have. We could use the same transformation, this same transformation, and for I2 and I3 also we could do that, because if you use again for sigma xi xi, this transformation is for eta eta and zeta zeta, and for xi eta and eta zeta and xi zeta also you can use, because this transformation, and you will see that we get that. Okay, for I2 we get that, and for I3 we get that. Sometimes we use these tensor notations because it's short and it's easier. Okay, I, J, I, J, I, J, J. I, J means, for instance, 1, 2, and 3. I and J change between 1, 2, and 3, 1, 2, and 3. So we could put for IJ, for instance, 1, 2, 2, 3, and 3, 1. And for II, obviously, it will be 1, 1, 2, 2, and 3, 3. So we get this will become equal to that. So that's how we could prove. Also for I3 we could prove that, because we can get a sigma x6, sigma y, etc. for the this coordinate system as well, and use this expression to substitute for it, and we will get it. Okay, we will get the result and show that I2 and I3 also are invariants. Here I have tried to show you how this transformation occurs. Okay, using this transformation, we are changing from this set of axes to another set of axes. So our state of stress, which was originally like that, will be like this, because it is using these axes. So these stresses will be, not the stresses, but the invariants will be the same. I1, I2, and I3 will be the same. Their values will not change. Okay, so and we have proven that. Okay, we have proven that these invariants are useful for us. You will see later that we make use of these coefficients.